Hey everybody, Mr. Sharkey back with another exciting chemistry video. I just wanted to talk about the key that I have for this bonding character review real quick. So if you looked over the key, hopefully it made sense, but in case it didn't, I took these 5 compounds and went ahead and did all the work for them, and this way we can just talk about them. So I think it'll be a little bit easier. I'll go ahead and highlight my 4 different compounds just so that we are all on the same page as to which one we're talking about. So let's start off by looking at PO4 3 minus. First thing that should stick out to you is that this has a charge of -3. So this is a polyatomic ion. As soon as you see that, you should look up on your periodic table. Naming this one's pretty easy. We just got to call it phosphate or the phosphate ion because it is one of our polyatomics. To draw the particle diagram for this one, we need to have a phosphorus surrounded by 4 oxygens, and this whole thing has a charge of -3, so we used a dashed line around it to show that the -3 charge is distributed across the whole thing. To look up what type of bond, we are focused on a bond between phosphorus and oxygen because that's the same type of bond we have all the way around the compound. So I'd look up the electronegativity of phosphorus and oxygen. I get 2.1 and 3.5 respectively. So to collect some data and predict what type of bond or what bond character we'd have, oxygen has an electronegativity of 3.5, so I could go over on my graph to 3.5. Phosphorus has an electronegativity of 2.1, so I'd then go up to 2.1. That puts me in the covalent category. So based on electronegativities, we would say that this is probably a covalent bond. The other piece of evidence we have, phosphorus and oxygen are both nonmetals, so we could use both of those pieces of evidence to help us prove that this is a covalent bond. Let's look at MgBr2. Drawing a particle diagram, magnesium in the middle, surrounded by 2 bromines. The name here is magnesium bromide. Hopefully that one looks a little familiar to us. We have a metal and a non-metal, so we'd use our ionic naming rules. Looking up our electronegativities, it looks like I forgot to put a little green mark here. Turns out that bromine is more electronegative at 2.8, so I go over to 2.8. Magnesium is less electromagnetic at 1.2, so I go up to 1.2. That puts me solidly in the ionic category. So based on electronegativity, I have an ionic bond between magnesium and bromine. That means that the bromine, which has a higher electronegativity, is going to pull the electrons closer to itself, forming an ion, so it'll actually have a negative charge when everything is said and done. OSO4, I think, is the first kind of tricky example because we have a metal and a non-metal. So when we name it, we could call it osmium oxide. When we draw it out, it'll look like this. But when we actually look at the electronegativities, we see that osmium has an electronegativity of 2.2. Oxygen has an electronegativity of 3.5. If we graph this one out, we'd see that we end up in the covalent category. So based on the electronegativity data that we've been given, this seems like it would be a covalent bond. And that would be the answer we would expect you to put on an assessment. Electronegativity data is going to be the most important. That's the strongest data that we have, so that's the one we need to use there. Looking at copper and zinc here, the electronegativities of both are pretty low. So when we graph it out, we end up here in the metallic section. So based on electronegativity, those would be metallic. We haven't talked about naming metallic compounds, so I wouldn't worry about the name on this one. NaOH, hopefully OH sticks out to you as one of our polyatomics. That shows up pretty often. I'm realizing I forgot to put the name, so we can throw that in. It would be sodium hydroxide. This one's a little bit interesting because now instead of just having one bond, we actually have 2 different bonds we need to focus on. So the bond between sodium and oxygen, the bond between oxygen and hydrogen. That's oversimplifying a little bit because really it's our sodium and our hydroxide. But once we start talking about polarity, it'll make a little bit more sense why we can just focus on sodium and oxygen. So let's look at that sodium-oxygen bond first. Oxygen has an electronegativity of 3.5. Sodium has an electronegativity of 0.9. That puts us solidly in the ionic category. The other reason is that we could tell it's ionic is because we have a polyatomic ion involved. So that should be a huge flag for us. The last thing we're going to look at is this bond between oxygen and hydrogen. Oxygen has an electronegativity of 3.5. Hydrogen has an electronegativity of 2.1. So when I graph it out, that puts me in the covalent category. So based on electronegativities, we could say that this bond was covalent. If this type of question were to show up on an assessment, we would ask you specifically which bond we wanted you to talk about, or both. So if we wanted you to focus on the bond between just the sodium and the hydroxide, you'd be able to tell us it's ionic and give us your reasoning. If we wanted you to focus on just the oxygen-hydrogen bond, we'd tell you that's the one we wanted you to focus on. I figured this video might help as you're trying to break down exactly what the key is telling you. So I'm going to end it here. If you do have more questions, feel free to reach out to me or to your chemistry teacher. Thank you very much. Have a nice day.